What if I told you that one of the most mind-bending experiments in quantum physics, one that supposedly proves particles can influence the past, is actually based on a widespread misunderstanding? For years, the delayed choice quantum eraser has been presented as evidence that measurement in the future can retroactively change what happened in the past. Science communicators, including some of the best physics channels on the internet, have gotten this experiment wrong. The idea has been repeated so often that it's become accepted as fact. But here's the truth: there's no time travel, no retroactive influence, and no violation of causality. Today, we're going to break down exactly where the confusion comes from, why the experiment seems so paradoxical, and what's really happening when quantum particles appear to receive information from the future. By the end, you'll understand why this experiment, while genuinely strange, doesn't require us to throw out everything we know about cause and effect.
To understand where the quantum eraser confusion begins, we need to start with the foundation, the classic double-slit experiment. Richard Feynman famously said of the double-slit experiment that it has in it the heart of quantum mechanics, and in reality, it contains the only mystery. The mystery he was talking about is superposition, which in the double-slit experiment means a superposition of a single particle traveling through both of the double slits at once. The experiment hints that, prior to detection at a screen, a quantum particle plays out all possible realities that may lead to that one measurement result. The shadow of these overlapping realities, these interacting trajectories, is cast on the screen in the form of an interference pattern. But if you prune the reality tree early, say by making a measurement at one of the slits, the final pattern of particle locations reflects that change. It's as if measuring which slit the particle went through collapses the wave of possibilities into a single definite path.
Let's think about what we expect to see in the basic setup. We need some light and two very narrow openings that we can shine that light through. What happens depends on how we think about light. On the one hand, we know that light is a wave in the electromagnetic field. Like any wave, it should produce interference patterns as components of the wave passing through the different slits overlap, stacking up constructively in some places and canceling out destructively in others. At the wall where we detect the light, we get the classic double-slit interference pattern, with its characteristic bright and dark bands.
On the other hand, we also think of light as particles, which is fair because the classical electromagnetic wave is actually made up of indivisible quantum particles that we call photons. An intuitive but naive picture for particles is to imagine them as tiny balls. If you spray balls at a pair of slits, they should end up forming two piles corresponding to passage through each slit. But photons are really some weird in-between thing, neither purely wave nor purely particle.
If you fire individual photons one at a time, they do appear to make single hits on the wall, as though they were tiny balls. But after many firings, after thousands or millions of individual photon detections, the double slit pattern becomes visible. The standard interpretation is that each photon really passes through both slits as a wave, and then the final destination of the particle-like detection is determined by the interference pattern made by that wave.
In quantum mechanics, we say that the position wave function of the photon passes through both slits, or that it exists in a superposition of both trajectories, and in fact, of all possible trajectories that could reach the wall. But when the wall measures the photon location, that superposition collapses, and a single position is chosen. Even then, the path the photon took to get there remains fundamentally undefined. It didn't take one path or the other. It took both, in some sense.
If you want to know the path taken, you have to measure it before the wall. For example, you could place a detector at the slits,
that registers the passing photon without actually stopping it. Essentially, you're collapsing the position wave function at the slits, not at the wall. Now that you know which slit the photon passed through, everything you see after that has to be consistent with it only passing through that slit, which means no double slit interference pattern.
Here's a common misconception that's important to clear up. Many people think that if a photon passes through just one slit, it lands ultimately just like a classical particle, forming a single pile of points behind that slit. But actually, single slit interference has its own characteristic pattern. It looks somewhat similar to double slit interference, but if you compare them side by side, you can see the difference. Single slit interference still has dark fringes where photons rarely land, but just not as many as double slit interference. This is a form of Fraunhofer diffraction, with the edges of the slits causing the interference in this case.
So photons keep behaving like waves even if we measure which slit they traversed. The key difference is that the pattern changes from the multi-banded double slit interference to the broader single slit diffraction pattern. The transition from double to single slit interference occurs when we make what's called a which-way measurement, determining which path the photon took. That's weird enough, but at least in this case, we have a sensible causal ordering. You make the measurement first, it collapses the wave function, and that stops it from forming a double slit pattern further down the line. Cause precedes effect, just as it should.
Things get dramatically weirder in the case of the delayed choice quantum eraser. In the classic experiment, performed by Kim and collaborators in 1999, the photons passing through the slits are cloned using a special crystal called beta barium borate, or BBO crystal. This crystal converts each incoming photon into a pair of nearly identical outgoing photons that are quantum entangled. This is the crucial element that makes the experiment so counterintuitive.
The key is that both photons in this entangled pair carry the which-way information. They both somehow know which slit their progenitor photon passed through before the BBO crystal duplicated it. Now we send one of the new pair, let's call it photon A, to our usual double slit detector to be observed by Alice. The other photon, photon B, goes to Bob, who has a choice. He can extract the which-way information, determining which slit the original photon came through, or, alternatively, he can choose to erase that information, making it impossible to determine which path was taken. The device Bob uses is conceptually simple. The path of photon B depends on which slit it came through, so Bob can place a detector on both possible paths and see which one is triggered. This is the measurement scenario. But Bob can also choose to scramble the which-way information by recombining those two paths so there's no way to tell them apart anymore. This is the erasure scenario.
Here's where things get bizarre. The result of the Kim experiment and similar experiments that followed is that if the which-way information is measured from photon B, then photon A acts as though we also measured which slit it came from, even though nothing directly interacted with photon A. Alice sees that those photons whose twins were measured fall according to a single slit pattern. But if the which-way information in photon B is scrambled and erased, Alice sees the corresponding photons landing according to the classic double slit pattern. It acts as though photon A did pass through both slits.
It's like we changed photon A's behavior without actually touching it, only by measuring its distant twin. This is already strange enough, invoking the spooky action at a distance that Einstein famously objected to. But if that wasn't weird enough, in the Kim experiment, the choice of whether to keep or discard the which-way information in photon B is made after its entangled partner, photon A,
has already reached its detector and been recorded. That makes it seem like photon A landed according to a choice that hadn't been made yet, a decision that lay in its future. And this has been referred to as retroactive causal influence, or retrocausality. And it's what makes the delayed choice quantum eraser so profoundly befuddling. It seems to suggest that the future can reach back and influence the past, that quantum mechanics allows information to flow backwards in time. To explain how we can get around this apparent paradox, let's look at an analogous experiment that can be done with relatively simple equipment. When we say it's analogous, what we mean is that it's mathematically equivalent. If you looked at the mathematics of the original experiment versus this simplified version, the equations are exactly the same except for how you label a few things. That's not to say that this experiment is as impressive as the other one, because the original involves actual quantum entanglement of photons, whereas this simplified version uses a clever trick to kind of mimic entanglement without actually creating entangled photons.
Here's the setup. We have a laser and a double slit, just like in the classic experiment. In the original Kim experiment, for every photon A that goes through the slits, they make a photon B, which knows which slit photon A took. Photon B is what stores the information about which way photon A went. In our simplified experiment, we need some other way to store that which way information.
The solution is remarkably simple. We place filters in front of the double slit, 2 different filters in front of each of the slits. In front of the first slit, we place a horizontal polarization filter. In front of the second slit, we place a vertical polarization filter. Now we know that any light that makes it through this double slit is marked. If it's horizontally polarized, it must have come through slit 1. If it's vertically polarized, it must have come through slit 2. In other words, the polarization is what's marking whether the light went through slit 1 or slit 2.
This is convenient because we can use a special crystal called calcite to split the light according to its polarization. Calcite has a very nice property. When oriented at a particular angle, it splits light into 2 beams based on polarization. These 2 beams of light represent the 2 possible paths from the double slit experiment. If the light is vertically polarized, it came from one slit. If it's horizontally polarized, it came from the other slit. When we examine the pattern, we see that the light in the top beam only went through one slit, and the light in the bottom beam only went through the other slit. So we expect that each of these patterns will be single slit patterns, not double slit patterns. And indeed, if you look closely at them, you can see that they are. Each shows the characteristic single slit diffraction pattern. The calcite oriented this way is acting just like Bob's which-way measurement, collapsing the light into single-slit behavior. But here's where it gets interesting. If we rotate the calcite by 45 degrees, something remarkable happens. This new orientation is going to act like Bob's erasure measurement, and we're going to recover the double slit pattern. When the calcite is rotated to this new angle, it splits the light into 2 beams again, but now we'll call them the plus beam and the minus beam. The critical difference is how the polarized light gets sorted.
With this 45-degree orientation, vertically polarized light doesn't all go to one beam. Instead, half of the vertical light goes to the plus beam and half goes to the minus beam. The same thing happens with horizontal light. It splits 50-50 between plus and minus. This is crucial. Now think about what this means for light that goes through our marked double slit. Light from the first slit is horizontally polarized, and light from the second slit is vertically polarized.
Previously, our calcite was letting us measure the polarization, and therefore determine whether light went through slit 1 or slit 2.
But now with this 45-degree orientation, the calcite takes light from the first slit and gives it an equal probability of ending up in the plus beam or the minus beam. The same thing happens with light from the second slit. So now, just looking at which beam the light ends up in isn't enough to tell us anything at all about which slit the light came through. The calcite has scrambled up the light from both paths. It has erased all the information we had encoded by marking the paths with polarization filters.
So what do we expect to happen? When we look at the pattern, we see not one, but two double-slit interference patterns, one in the plus beam and one in the minus beam. If we use the calcite in its first orientation, we're using it to measure which way the light went, and that collapses the light into single-slit interference. But if we use the calcite in the 45-degree orientation, we're using it as an eraser. It erases the information about which slit the light went through, and so we recover the double-slit pattern.
If you look really closely at these two double-slit patterns, the plus pattern and the minus pattern, you'll notice something crucial. They don't exactly line up. In fact, they seem to be offset from each other by exactly the right amount that if you superimpose them, the combination looks like a single-slit interference pattern. This is the solution to the entire paradox. This is the key insight that resolves the apparent time travel.
Let's go back to the original experimental setup to understand why this matters so much. In the chem experiment, photons are cloned by the BBO crystal, and the which-way analysis is done with only one of those cloned photons, photon B. Just as our simplified experiment sorts the photons into two interference patterns, the plus and the minus, the original experiment sorts the B photons into different detector bins.
For the measurement case, where Bob checks which path photon B took, those bins tell you which slit the corresponding photon A also went through. For the eraser case, where Bob scrambles the which-way information, there are still two bins, two detectors that can register photon B, but there's no which-way information in how photons are sorted into them. Here's the critical point that's often glossed over in descriptions of the quantum eraser. Alice, who's detecting photon A, never sees a double-slit interference pattern in her data initially. At first, she sees just a blob of positions for all the photon A detections. It's a featureless spread of dots with no clear pattern. Then Bob comes and tells her which of those photon A detections had a twin photon B for which the which-way information was measured and for which it was erased. The measured cases where Bob determined which path photon B took are still just a blob when Alice looks at only those detections. It's basically a blurry single-slit interference pattern. Now, the sum of all the cases in which the which-way information was erased is also a very similar mess, another blob with no clear features. So Bob also needs to tell Alice which of those erased photon Bs ended up in each of his separate eraser detectors.
Only then, only after Bob communicates this information to Alice through normal light-speed limited communication channels, can Alice disentangle the featureless blob of photon A positions and see interference bands. Her patterns, when sorted according to Bob's detector results, look a lot like our calcite experiment. Clear peaks and valleys that are slightly offset from each other. And when you merge them back together, you get a featureless pile, the original blob.
This is the resolution. The solution is that Alice always sees the single-slit pattern initially, and that's regardless of what Bob chooses to do on his side. There's no instant change in her data when Bob makes his measurement. But a single-slit pattern is really just two double-slit patterns superimposed on top of each other, the plus version and the minus version that are slightly offset.
If Bob happens to do the eraser measurement, then he and Alice can meet up afterwards and sort Alice's photons into the plus and minus groups based on which detector registered photon B. Only then do they find those two double-slit patterns hidden in the data. In our simplified experiment, we did this sorting with the calcite crystal, but in the real version of the experiment, it just looks like post-processing the data, sorting the detections after the fact to reveal the patterns that were hidden all along.
So instead of Bob's erasure measurement instantly uncollapsing the wave function and turning single-slit interference into double-slit, you only see this effect of his measurement much later, once he and Alice get together and sift through the data. There's no faster-than-light influence, no retroactive causation, no information traveling backwards in time.
The story told by the retrocausal interpretation of the delayed choice quantum eraser is that Bob's choice of measurement retroactively influences where Alice's photon lands on her detector. But here's something fascinating that completely undermines this interpretation. The same logic works the other way around. The position of photon A measured by Alice absolutely influences where photon B can be detected by Bob.
Imagine that Alice measures her photon and it happens to land at a particular position on her screen. That position lines up perfectly with the plus double-slit pattern, but falls in a dark fringe, a minimum, of the minus double-slit pattern. Now, after that, Bob measures his photon B, and he chooses to do an erasure measurement. That means there are two possible outcomes. He could detect it in his plus detector, or he could detect it in his minus detector.
But could he really get a plus result? That wouldn't be consistent with the result that Alice has already obtained. Her photon landed in a location that corresponds to a bright fringe in the plus pattern, but a dark fringe in the minus pattern. So actually, Alice's result forces Bob's result to also be plus. If Alice's measurement happens first, then her outcome is what determines what will happen when Bob does his erasure measurement. In other words, Alice's outcome is what forces Bob's to happen the way it does.
But here's the twist that makes this even stranger. Does Alice's measurement always happen first, or does the order depend on your frame of reference? Due to the relativity of simultaneity in special relativity, it's possible to set up this experiment so that Bob's detections actually happen before Alice's in certain reference frames, just by changing the path lengths for each section, or by considering observers in different states of motion.
If we do that, we expect exactly the same experimental result. The same interference fringes are revealed when photon A data is filtered according to where photon B landed in the eraser detectors. In that case, from one perspective, it seems that B caused A, but with the same result as when A caused B. This makes it extremely difficult to assign a causal power to either case in any absolute sense.
It's also hard to even imagine a causal path connecting Alice and Bob's observations beyond the sort of spooky action at a distance that Einstein so objected to. That said, there is a way to explain the correlation between Alice's and Bob's observations that doesn't need to assign a causal direction at all, that doesn't require influence flowing forward or backward in time.
It all depends on what mysterious property really determines how our photons get sorted into the two detectors in the quantum eraser, or how they get sorted into the two interference patterns by the calcite crystal in our simplified experiment. What property is that? It's quantum phase, the relative phase of the wave function, which is determined at the moment the photon passes through the slits, not when it's later detected. The correlations between Alice and Bob's results were established back at the source, when the entangled photons were created and when they passed through the marked slits.
The key insight is that quantum entanglement doesn't transmit information faster than light. It creates correlations between distant measurements,
But you can't use those correlations to send a signal. Alice can't control what Bob sees, and Bob can't control what Alice sees. They both see random results that only make sense when they come together later and compare notes. The delayed choice quantum eraser is weird, but it's no weirder than any double-slit experiment or any experiment involving quantum entanglement. There's no retroactive causation, no influence from future to past, no violation of the principle that cause must precede effect. What there is quantum superposition, quantum entanglement, and the genuinely strange correlations that quantum mechanics predicts and that experiments confirm.
The apparent paradox arises from a misunderstanding of what Alice sees before and after Bob's measurement, and from forgetting that the hidden double-slit patterns only emerge after classical information is exchanged between Alice and Bob. Once you understand that Alice always initially sees a featureless blob that can be decomposed into offset interference patterns only after Bob shares his results, the mystery of retroactive causation evaporates. What remains is still mysterious, still profoundly quantum, but at least it doesn't require us to throw out causality itself.